technical difficulties, but it's the first hybrid talk, so I'm glad to be here. I'm glad everyone's here, and I'm glad that people are able to join on Zoom as well, because I'm really excited to talk about recent results from the SH0ES and Pantheon+ collaborations. You may have heard of SH0ES. I'm hoping that by the end of this talk, you'll be familiar with Pantheon+ and their relationship, which are now kind of tied at the hip. And more generally, if I have some time, although I don't want to keep you past, we'll just talk about generally what Type Ia supernovae can do in cosmology going into the future. So the SH0ES and Pantheon+ collaborations have been pushing for the last year, well, more than a year, but the last year has been a real push to get a bunch of papers out. I'm going to be just touching upon these as much as I can today, although obviously I won't be able to go into too much depth. But I wasn't kidding when I said we've been pushing for the last year. Actually, the final cosmology paper came out the day that my child was born. And now that she's here with us, she's officially Brazilian and had her first churrasco. So this has been an exciting trip for us. I think we can all learn a thing or two about selling our science, and there's been this really great blog called Starts with a Bang by Ethan Siegel. He dives into all things cosmology and astrophysics, and he does a really good job of selling the Pantheon+ supernova study. And I'm just going to steal a couple of quotes from his article, like, with 1,550 individual Type Ia supernovae that span 10.7 billion years of cosmic history, the latest Pantheon+ results are a feast for the cosmologically curious. And it's arguable that the most impressive of the heavy lifting done by the Pantheon+ team is the remarkably tiny errors and uncertainties that exist when you look at the data. So if that doesn't make you want to think about systematics, I don't know what will. So today, I'm just going to briefly talk about how Type Ia supernovae fit in as a pillar of cosmology and the history of Type Ia supernovae and how they've been used. I'm going to talk about a number of advancements that we've had to make in order to push down the systematic floor in our analysis. And then I'm going to briefly touch upon the results that we found for Pantheon+ and for SH0ES, where the SH0ES team has measured H0. And we're going to touch upon the H0 crisis, which has now crossed the ever-important 5 sigma threshold with Planck. And then if we have time, I'm going to talk about the dark energy survey and LSST. So very briefly, on the left here, I'm showing distances versus redshift in the top panel for the supernova samples that discovered dark energy. You can see a low redshift sample and a high redshift sample. And then in the bottom panel, you can see the residuals to various cosmological models. So the idea, the name of the game today is to put supernovae on the Hubble diagram and compare them to cosmological models like the standard model of cosmology, lambda CDM, where a couple of key assumptions go into that, those being that the universe is homogeneous and isotropic on large scales, and in lambda CDM, that dark energy behaves like a cosmological constant, although we'll be able to test that. So Type Ia supernovae are especially good probes of cosmology and of dark energy because they probe an extremely large span of distance and redshift, going all the way back past 10 billion years, more than 3/4 of the way back to the Big Bang, which means we get to see the universe grow from being matter-dominated to dark energy-dominated, and that's what makes them such a unique probe of dark energy. In doing that, we've compiled samples. So we go and collect Type Ia supernova with a telescope, but as I showed on one of the first slides, we have to combine supernovae at low redshift and high redshift, which are typically done on different telescopes, although not always, but generally speaking, over the last decade or more now, we've had to compile samples at various redshift ranges by different telescopes, and these are samples that have been adopted by the cosmological community. Each of these has over 1,000 citations, and I would call a pillar of cosmology. More recently, the Joint Light Curve Analysis analyzed 5 different surveys, 700 supernovae, and the Pantheon analysis, not to be confused with the Pantheon+ analysis, which is what I've been working on, is 6 different surveys and 1,000 supernovae. So concordance cosmology in dark energy density and matter density, it's familiar to many of you. We, from many different cosmic probes, believe that the universe is flat, dominated by dark energy today, and has roughly a third of the energy density of the universe attributed to dark matter. And I'll note that if you've been looking at these concordance cosmology plots over the last 5 or so years, you'll have noticed that it's the Pantheon the Pantheon supernovae that are used typically when analyzing supernova contours. But of course, we know that there are many unexplained questions in concordance cosmology and lambda CDM. Those being, what is the cause of the cosmic acceleration or dark energy? Is it the vacuum energy, or is it a cosmological constant or something else? Is it evolving? Is, in fact, the universe homogeneous and isotropic? The cosmological constant problem, of course, 120 orders of magnitude. Observation is smaller than the theoretical expectation. And ultimately, when we test when we do an end-to-end test of the universe, that being a measurement of H0, which I'll be talking about, it doesn't pass. We also have this S8 curiosity, which may or may not be related. I'm not going to have time to touch upon it today, but we'll dive in on the H0 crisis. So this in the middle here is a baby growth chart. As you can tell, I've been thinking about babies a lot. So the H0 crisis, the Hubble constant crisis, you can think of as a comparison of the universe as we know it when it was a baby from the cosmic microwave background, specifically measurements from Planck. You can take some model of the universe and predict what the expansion rate of the universe should be today, and we compare that to direct measurements using absolute distances in the local universe by the SH0ES team. We call that the distance ladder approach. And as of 2016, the measurements of the expansion rate of the universe today didn't match up between Planck and SH0ES at about 3 sigma, where Planck gets a low value of 67 and SH0ES gets a high value of 73. So briefly, the cosmic distance ladder, the SH0ES approach, utilizes geometric distances in the bottom rung of the distance ladder. Those geometric distances can come from parallax, they can come from masers, detach eclipsing binaries, many different sources as different cross-checks on absolute distance. And those absolute distances are used to calibrate the Cepheid period luminosity relation. That is a relation that allows us to calibrate the Cepheids as standard stars. That is, we can infer their relative brightness or their relative distance, and we can calibrate that to an absolute geometric distance in the bottom rung. Once we've done that, we can transfer that calibration to the Type Ia supernovae. The reason we have to use this laddered approach is because the Cepheids can only be seen out to roughly redshift 0.01, and the supernovae, there's just simply not many supernovae out. We haven't had enough supernovae in the bottom rung of the distance ladder, so we use the Cepheids to transfer the calibration to the supernovae in the second rung of the distance ladder, which is even still the rate-limiting step. So we have 42 supernovae in the middle rung of the distance ladder. Those are supernovae that went off in galaxies that are visible from the Hubble Space Telescope, from which we can measure Cepheids and that have had a supernova go off in them. So that's the rate-limiting step. And then the last step is, once you've calibrated the absolute luminosity of the supernovae, you can measure them out into the Hubble flow and measure the Hubble constant or the expansion rate of the universe, locally and today. Now, in 2016, in the last SH0ES analysis, the second and third rungs of the distance ladder were treated separately. And the major point that we've done here is to combine them in what we're now calling the Pantheon+ sample of supernovae. That is, the Pantheon+ sample goes down to redshift essentially 0. It contains the most nearby supernovae that we have and goes all the way out to redshift 2, 5 orders of magnitude. And most importantly, we propagate all sources of systematic uncertainty in the entire sample simultaneously, which means we're propagating the uncertainties in both the second and the third rungs simultaneously. I'm going to dive in on that a little bit more. Now, in 2016, one of the big benefits, and still a big benefit of the analysis, is that the distance ladder approach works such that if there's anything that goes wrong in any of the steps of the distance ladder, as long as it goes wrong in any other step of the distance ladder, so for example, if you get your supernova magnitudes wrong by 100 magnitudes, it doesn't matter as long as you get them wrong in the second and third rungs of the distance ladder. It'll cancel out in the calibration. So the important thing is to be able to characterize the differences between the second and third rungs of the distance ladder, propagate systematics that affect the different rungs in different ways. Those are the potential sources of systematics that can creep into your measurement and affect H0. And so we've compiled the Pantheon+ sample, which is 1,701 light curves of 1,550 individual supernovae from redshift 0.001 extremely nearby to redshift 2.3. And that means we've compiled 18 different surveys, 25 different photometric systems, and 105 filters, which means we now have an average of 2 photometric systems, calibrations, for each supernova that is in a Cepheid host. So that's 80 light curves in 42 hosts. And that's especially important because one of the big systematics in supernova cosmology that we worry about and that we lose sleep over is calibration. Are you getting the absolute magnitude correctly, or the relative magnitudes correctly, between different samples? So having 2 photometric systems for every, on average, for every Cepheid host supernova is important for beating down that potential source of uncertainty. And then lastly, as I said, the Cepheid calibrator supernovae are analyzed simultaneously with the supernovae out into the Hubble flow, propagating systematics simultaneously. Now, there's been updates to the SH0ES sample as well. The second rung of the distance ladder from 2016 to 2021 has gone from 19 supernovae in that second rung to 42. This is the rate limiting step, and you can see how long it's taken to collect them, and you can sort of forecast when the next big update from SH0ES or whoever's doing this next is, and it's going to be a while. The next time we double our sample like we've just done is going to be a decade maybe, right? Because we have to wait for supernovae to go off in very nearby galaxies. We've also more than tripled the number of Cepheid calibrators in the main calibrating host NGC 4258, and we've revamped and improved the pipelines for the Cepheids and propagating systematics as well. So today, I'm going to make 2 big claims. On the left-hand side, the claim in Pantheon+, I'm showing you blinded contours for the equation of state of dark energy and dark matter, comparing the original Pantheon from 2018 in yellow to my most recent result, and I'm claiming that we've improved our figure of merit by a factor of 2. So you should question that, and hopefully I'll be able to convince you of that today. And then on the right-hand side, the SH0ES team is now claiming a 5 sigma discrepancy, or a 1 kilometer per second per megaparsec measurement of H0. Okay, so just a very brief review of how we use the Type Ia supernovae. We correct their apparent luminosity, their observed apparent luminosities for stretch and color luminosity relations, alpha and beta. We do that by fitting light curves. On the left, I'm showing light curves from the dark energy survey. And we use relations like the stretch relation, where we know that less luminous supernovae fade faster than more luminous supernovae. And after doing that correction, we can get the dispersion in the measured luminosities or distances down to about 10%. And it's the ratio of the intrinsic to the apparent luminosity of the Type Ia supernova that gives us the luminosity distance. We then separately measure a redshift from a redshift follow-up program, ideally from the host galaxy, but can be measured from the supernova, and that's independently measured. And then once you have the redshift and the luminosity distance, you put them on the Hubble diagram. Although it's a little bit more complicated than this. First, we model the demographic selection and completeness. We need to find optimal redshifts, not just the redshift. We need to count for things like peculiar velocities. We want to know if the galaxy is in a group. We want to, of course, know if it's a Type Ia supernova or not. We only care about the Type Ias that follow this specific relation. We do the cross-calibration of the telescopes, instruments, filters, and surveys using all sky instruments. We have to model the surveys themselves in order to correct for biases that we expect from individual surveys. We compile the light curves, fit the light curves, correct for the biased expectations in our observables, propagate systematics through every one of these steps, and propagate those systematics into the Hubble diagram before we measure cosmology. And when we measure cosmology, over the last almost 10 years now, we've been measuring extremely well and better over the last 10 years. But one thing you'll note is that each year, so in the joint light curve analysis from 2014, in my analysis from 2018 of the Dark Energy Survey, and the original Pantheon, systematic errors have been larger than the statistical errors by 60%, 10%, and 20%. That's not to say that the methods haven't gotten better. It's just that we've had to push the systematic floor down as our statistics have been getting better. And that's been a large portion of the challenge that we've been working towards in order to make the most of the Pantheon+ sample. So I'm going to talk about some of these advancements very briefly. A lot of this work has been done by young, early career scientists. I'm going to be highlighting them in their pictures, so hopefully you'll get to know them as well. So one of the big things that has been plaguing supernova cosmology up until recently is what we call the mass step. The mass step is a correlation between the supernova luminosity and the host properties. That is, the luminosity that we infer and the properties of its host. Namely, it's been seen as a function of mass. It's been seen for over a decade. There hasn't been a good, concise explanation for it until recently, and we claim that we've solved it, which is coming from the fact that we have a new signal in our data. Because we have the largest data set ever compiled, we can actually measure the mass step, the correlation between the inferred luminosity and the host galaxy properties, as a function of the color of the supernova. And the red supernovae are over here on the right side of the diagram, the blue supernovae on the left side of the diagram. And what we find is that the blue supernovae do not exhibit this additional mysterious correlation. It's only the red ones. And what we immediately thought from this plot was, well, it's the dust that's causing whatever is this correlation with host properties. And we came up with a model for it. Our model explains the fact that we do not see a correlation for the blue supernovae, and it's only the extinguished reddened supernovae that have this correlation, and it grows as you have more and more dust. And there's a couple of key points of this model and key predictions that have been tested already, which is that this model predicts large variations in the dust attenuation law, that is the color luminosity relation of the dust itself related to the dust particles and so on. It predicts a very large variation in these dust particle properties, and that these properties vary with the mass of the galaxy. They're correlated with the mass. Otherwise, we wouldn't have seen this correlation. They can correlate with other properties as well, and we've seen that as well. But in order to explain the mass step, they have to correlate with mass, and that has been seen as well. And then lastly, if you're observing the supernova in the near-infrared bands, you're much less sensitive to dust, and you should not see a mass step at all for any supernovae, and that's what Ariel Gubar's group has found. So Ariel Gubar is the leading dust supernova cosmologist, and Johansson et al. Sees all three of these predictions in the single largest and highest quality near-infrared data set, so they claim it's fully consistent with our model. So this is one of the major sources of systematic uncertainty that we claim to have beaten down for supernova cosmology. Near-infrared. So all of this is optical bands. They have a separate, it's harder to collect in the near-infrared. You have to go to space and stuff like that. So it's harder to collect a sample. So their sample is much smaller than this, but it's the highest quality data set that exists, and they don't see a mass step. So they're essentially seeing through the dust, and therefore they're not getting this additional correlation in their data. Another big undertaking that we've had to do is the cross-calibration of the 18 different samples, the 105 different filters. I mean, this was really, I mean, there's no other way to say it. It was a headache. And we utilize the Pan-STARRS All-Sky Catalog. This is, the Pan-STARRS telescope has measurements of stars across the entire sky, and it overlaps with all of the 18 different surveys that we've combined with. So we can leverage Pan-STARRS calibration and their Pan-STARRS uniformity across the sky, and all of the new surveys like the Dark Energy Survey, which overlap with Pan-STARRS and themselves have a very good calibration. We can refine those calibrations by combining the data sets, but also, most importantly, we can recalibrate the low redshift samples. The old samples that have old calibrations, we can use the new samples to pin down those calibrations. And in doing so, we end up with a covariance matrix. It's a 105 by 105 covariance matrix that characterizes the covariance in the calibrations, in the 0 points of each of the filter magnitudes. And the most important piece of this is that we have to characterize this covariance as a function of survey, but that the oldest surveys, which have had the worst calibrations and have the largest covariances, are predominantly in the second rung of the distance ladder, or at low redshift, because that's the regime where we're starved for statistics. So we have to look to the older samples to get those supernovae. And so in calibrating them, we want to make sure that we understand their calibrations and the redshift dependence, because they're all the old surveys, less well calibrated, but they're all at low redshift. So anything that has a redshift dependence, we're worried about. It can look like cosmology, and I'll talk about that briefly. Another piece that we've worked on that has drastically reduced our error budget is a paper that I wrote with Sam Hinton and Dan Skolnick, which I called Binning is Sinning Supernova Version. So in exoplanets, there was a Binning is Sinning paper by David Kipping, and Kate Story-Fisher and David Hogg wrote one on large-scale structure. And if there's nothing that you take away from this talk other than this, I'll be happy. Please don't bin your data if you can avoid it. Don't bin your data. And here's why for supernova cosmology. Well, firstly, let me just say, the original Pantheon in 2018 binned their data set as a function of redshift. The Vera Rubin LSST science forecast, science requirements document binned its data set, or its simulated data sets, as a function of redshift. They followed the Pantheon analysis. Also, the joint light curve analysis, actually, they didn't bin, they smoothed, but that's the same problem as a function of redshift. And I did this, whoops, a couple years ago. So it boils down to the following. Binning loses information. And in supernova cosmology, we have perturbations to our analysis when we characterize systematic uncertainties. Here is one example. It's a difference in distance between two different models of Type Ia supernova. But the point is, it's a perturbation to our analysis, and we end up with different distances, and that's always of a concern. But if you plot those difference in distance as a function of the color of the supernova, you see all of this like funky, beautiful, whatever you want to call it, structure. And if you bin your data set down here, this is the same data, but now binned as a function of redshift, you can see something that could be confused with the cosmological signal. And that's the main takeaway is there's no cosmology that's really going to change supernova colors. There is a cosmology that can look like this, though. Let me try to explain this in a bit more rigorous method. If I take this method of measuring systematic uncertainties by Faccioli, it's, so if we essentially minimize delta in our fit, so delta is the nominal distances, or magnitudes, distances, and some perturbation to our analysis times the size of the systematic. So let's say I don't believe I understand my calibration by 1%. I will put a prior on S, the size of the systematic, to be 1%. So the size of the systematic can be no larger than that from my own knowledge. But the data can actually constrain down the size of S. So S is a free parameter that can be constrained by your data. And if we compare these two pieces to the cosmological model and minimize, we find the following. So cosmology, W and omega matter, and SH0ES, this free parameter describing the size of your systematic uncertainty. If you don't bin your data set, you get the blue contour. If you bin your data set, you get the black dashed contour. So there's information in the data here. This is a simulation, so it's designed to do this, but it shows the impact of binning your data. You can actually use the data itself to constrain down sizes of systematic uncertainties, but only if you don't bin the data. Here, this is a systematic that has a color dependence like the one I just showed on the last slide. Now, if your systematic is purely redshift dependent, there's nothing you can do. It can look like cosmology. That's a bit of a generalization, but generally, if your systematic is a redshift dependent systematic purely, like a systematic in measuring redshifts, then you don't get this benefit. And so what did that do to our error budget? For the astrophysics portion of our error budget, the binned uncertainty was, roughly 2%, went down to 1%. The calibration and photometry went pretty much cut in half. The survey modeling came down significantly. The redshift systematics did not. All in all, our error budget came down by a factor of 1.5 just simply from this key change to how we do the analysis. Now, it sounds trivial. In practice, it's harder because now we have a 2,000 by 2,000 covariance matrix that we have to invert, and there's a whole host of problems with that. But able to do it, you get this benefit. And it gets better because for LSST, you get the benefit that the systematic, quote unquote, self-calibration is what I'm calling it, grows with the size of your data set. The more data you have, the more ability you have to constrain down certain sources of systematic uncertainty. Of course, only if they're not a purely redshift dependent systematic. So these are simulations, so this one is designed to look like a cosmological signal, but you can see how for LSST, I'm actually not terribly worried about the systematic floor for supernova cosmology as some might think, although in measuring the redshifts, I am a little bit worried, but I think we'll be able to tackle that. So we've done a whole host of other advancements, and I think I have time to just summarize them very briefly. For Pantheon+ and SH0ES, we've done a full sweep of the redshifts, host galaxy assignments, and fixed some historical mistakes. That was work by Anthony Carr. Eric Peterson has done a comparison of the peculiar velocity maps that we use in making the optimal corrections to the redshifts that we use. We only want the cosmological redshift. We don't want redshift that is associated with pull from structure in the nearby universe. And he adds group information and shows improvements in the Hubble diagram. Brody Popovic and I have written 2 papers on supernova modeling, one on the survey modeling and one on modeling of the dust properties. And lastly, I've written a paper with Sasha Berger on worst case scenario, what if calibration was wrong by any of the surveys, what would happen? What would let's say we throw out our prior knowledge of how well we think the surveys are calibrated. We can actually leverage the fact that there are so many surveys. We have 18 surveys. So if one of them is miscalibrated, as long as it overlaps in redshift with some of the other surveys, you are actually able to use the other data sets to self-calibrate them. And this is something that H0 benefits from. So we can sleep at night when it comes to the H0 tension, although when you go out to higher redshift, where there's much less overlap between the surveys, because they're harder to find the supernovae, omega matter and W are not insensitive to calibration uncertainties. But when it comes to H0, I'm pretty happy to say that I'm not worried about calibration uncertainties for supernova relating to H0. So all in all, we push down the error floor. We have this large covariance matrix that we now use. It incorporates 115 sources of systematic uncertainty. And we have a new likelihood in Cosmosis and Cobaya. If you use those codes, you should be able to just plug and play with this. The supernova likelihood will take longer now because it's got to invert this large matrix, but you get the benefit of vastly reduced systematic uncertainties. And in fact, for the first time in a long time, we are not dominated by systematic uncertainties. As you can see here, our uncertainty on the equation of state of dark energy, we're now limited by statistics again. And this is what our new concordance cosmology plot looks like on the left, Pantheon plus in the red. And we find omega matter of 0.338 plus or minus about 2%. And when we fit for the equation of state W, we find that it is consistent with -1, and that the supernova contour intersects the Planck contour right at -1. We think that we have the best constraints on the potential evolution of dark energy. As I said, the supernovae cover such a large span in redshift and are especially sensitive to distances when the dark energy is turning on, when it's really becoming a dominant component of the universe, that we are the most sensitive probe to the evolution of dark energy, WA. Although it's not a great constraint, it's consistent with 0 at quite large error bars. But when you combine it with BAO and Planck, we do find a slightly negative value at 2 sigma, although 2 sigma, we're not saying anything. So on the SH0ES side, that is the Cepheids and the geometric distances side, they've done a similar approach to this covariance matrix approach, motivated by the supernova treatment as well. And so now what we're left with is actually like this distance ladder of covariance matrices. Basically, at this point, the name of the game in H0 is, do you understand your systematics? And that's what it's been all about. And that's why we claim a 1% uncertainty on, 1 kilometer per second per megaparsec uncertainty on H0. And that comes from the detailed treatment of systematics on the Cepheid side, which I don't have time to go into. But this distance ladder covariance matrix is also going to be available if you want to measure H0 and, for example, other cosmological parameters simultaneously. And so that's what we've done here. We now can measure H0 from the supernovae in the second and third rungs of the distance ladder, but also because the Pantheon plus sample goes out to redshift 2, we can measure Q0 or dark energy and all the nuisance parameters that go into the distance ladder approach. It's all happening simultaneously, and you can do it now too. And so what we find is that the supernova side comprises less than 1/3 of the H0 error budget, and that because we're rate limited by the second rung of the distance, actually, from the supernova, we are very much not dominated by systematic uncertainties when it comes to H0. So we are starved for statistics still in that second rung. That's the dashed lines out here further out. The systematic uncertainties are quite well controlled, as you can see all the different sources. And the bottom line is that for any systematic from the supernova side, and for that matter from the Cepheid side, it's really hard to get H0 below 72.5. without starting to throw out data. And so the SH0ES analysis claims a 1 kilometer per second per megaparsec uncertainty, a central value of 73, and that puts it at 5 sigma from the Planck value. They do that in lambda CDM, and from the Pantheon plus side, we go beyond lambda CDM. We examine WA, as I said. But from the H0 side, you might be led to think, oh, if I expand my parameterization for cosmology to include WA, you could end up with a high H0. And by that I mean Planck, if you allow WA to float, could give a high H0 in this gray contour here. But if you include the Pantheon plus supernovae and Planck, that is the uncalibrated, no Cepheids, just the relative from the Type Ia supernovae, with Planck, you get the dark blue contour. So the Type Ia supernovae actually do not permit a WA value that would allow for a high H0. Whereas when you combine the SH0ES Cepheid measurements with the Pantheon plus supernova, you get the high H0. That's the distance ladder method. So we conclude WA cannot resolve the H0 tension, evolving dark energy. We have a couple other recent papers that have come out that all kind of touch upon the robustness of the Type Ia supernovae in the distance ladder. On the left here, I'm showing a paper by Darcy Kenworthy. He does a 2-rung distance ladder. He's essentially throwing out the supernova and measuring H0 from the Cepheid distances, where the Cepheid distances only go out to redshift about 0.0. So they're heavily dominated by peculiar velocities. He's taken great care to account for the peculiar velocities, the systematics in the measurements of the peculiar velocities, and perhaps most importantly, the redshift selection function of the Cepheids that have been measured. There is no issue with a redshift selection function if you're not using the redshifts of the Cepheids, as is done in the normal 3-rung distance ladder. In that 3-rung distance ladder, you don't ever use the redshifts of the Cepheids. But for a 2-rung distance ladder, you do, and you have to be careful about the selection function. And that's what really limits. But he does get a high value and relatively competitive error bars. Now, on the other side, we did a 4-rung distance ladder. Why would you do a 4-rung distance ladder instead of a 3-rung distance ladder? Well, it allows you to transfer the calibration in the 2nd rung. Let's say you're worried about the selection of my supernovae in the 2nd rung of the distance ladder. Let's say you don't trust my dust model, you don't trust the masses of the galaxies and all these systematics that could affect the 2nd rung of the distance ladder. Well, you can use Cepheids to tie to surface brightness fluctuations. That would be this extra rung in the distance ladder. And the surface brightness fluctuation distances are different types of galaxies. They have different masses than the Cepheid galaxies. And they host different types of supernovae. So if you're worried about systematics associated with supernovae or their correlation with host properties, well, we have another sample where we've transferred the calibration in an extra rung, and we still get a high H0. Okay, so what could be going on? And I'm not a theorist, so I'm not going to dive into this too much here. But what could be causing H0 tension? Well, there's a great summary by Eleonora Di Valentino. I've worked with SH0ES. There's been papers by Wayne Hu, but they all kind of culminated in the sense that late universe physics are really hard to solve the H0 tension. Now, since Eleonora's paper, there's been very intriguing 3 sigma evidence for early dark energy in the ACT plus Planck, low L plus Planck lensing plus BAO. Important thing to note, there is no Planck high L in this measurement. They did not find a signal with high L. And so even Colin Hill suggests that this could be a sign of systematics in Planck, although still very intriguing, could be real. And then I think I saw on your schedule for talks a month or 2 ago, someone talked about this paper by Oliver Philcox using probes that are sensitive to pre-recombination physics. And he combines with, of course, the Pantheon plus supernovae, which are scale independent, I believe. And he finds a low H0 as well. Okay, so 10 minutes. You know what? I think I have time. Okay, I just don't want to keep people late. So I want to touch upon the dark energy survey. This is a really large analysis coming up that I'm leading. We already released our 3-year results using a spectroscopically confirmed sample that is just like what we did in Pantheon+, where the Type Ia supernova, we know that they are Type Ia because we've taken spectra of them, and we know from their spectra that they're a Type Ia. But this sample, in the 5-year DES sample, that's our final analysis, is the largest and deepest supernova sample from a single telescope, 1,650 supernovae from a single telescope. But they're photometrically classified. It's just too intensive to get spectra of them in real time. So we use machine learning methods to classify them as Type Ia supernovae. And for a while, this was thought that this could be one of the largest sources of systematic uncertainty, to use the light curves and some algorithm, and this has come a long way in the last 5 years, machine learning of classification. When we apply these, they just do phenomenally well. And this is what DES and LSST are going to be using for their classifications. And what we find is that systematics from contamination, or the classification systematic, is at most 4%, which is just tiny for what we had originally thought it would be. I would argue that Maria Vincenzi in DES has essentially solved photometric classification, of course, with the help of these really advanced machine learning classifiers. But basically, when you run a perfect classifier on simulations and compare to a neural network classifier, you get the same cosmology out, essentially. And the key point here is that even if you get the classification wrong, as long as you know that you're potentially getting it wrong, you give it a probability. You say, I think I know it's a 1A at 80% probability. As long as those probabilities are calibrated, you get unbiased cosmology. And that's the name of the game now. But they're all at 99%, purity. Like they get them right. They get it right. And that brings me to LSST. So LSST will really be a revolution. You've probably heard about it from weak lensing, but I want to give you some perspective for supernova. So in the blue is the Pantheon+ sample. That's just the redshift histogram. That's the number of supernovae as a function of redshift. Note that the y-axis here is a log scale. So the blue is Pantheon+. The red is dark energy survey sample. And in the black are the two fields for LSST. And you can just see we're going to be finding millions. And for comparison, the weak lensing analysis in the dark energy survey was 5,000 square degrees, and it's going to 18,000 square degrees of the sky. The supernova sample, the red curve, was 30 square degrees, and it's going to 18,000 square degrees. I mean, this is just mind-blowing for supernova people. We can't even fathom it really is just crazy. And so that brings us to what are the things that we can do with the supernovae. Up until now, we've been drinking from the proverbial watering hole, the Hubble diagram measuring dark energy and dark matter. And that essentially collapses the whole sky onto these two dimensions in the Hubble diagram. But when we start to look at the whole sky in different directions, we become extremely statistically limited. So we can start measuring proper motions, our local universe, our local structure. We can test isotropy. We can chop up our sample in different directions of the sky. We can measure the growth of structure S8 and test gravity, similarly to how the redshift surveys are going to be doing. In fact, I would argue maybe even better. We can test voids as well. Of course, there's strong lensing we're going to catch. There's other time domain probes. And we can get into some astrophysics as well. As I mentioned, we've already gotten to a little bit of galaxy dust. We can get into Milky Way dust. And then ultimately, we're going to have millions of supernovae across the sky, these precise distances to them. And we can start doing cross correlations with the weak lensing maps, the all sky maps. And we don't have to do tomographic bins. We have really good distances. So, in summary, exciting results like the one shown here are entirely possible from LSST and the Nancy Grace Roman Space Telescope. This is a little bit of a cheeky plot because I took their forecasts and centered them at the W0 WA contour that I found for Pantheon+. But if this signal is really real at 2 sigma, then LSST and Roman are going to find it. It looks like the H0 tension isn't going away, and LSST may provide cross-checks, but ultimately, we won't beat SH0ES for a while, right? We're really rate limited by the amount of supernovae in the local universe. One of the largest barriers to future supernova cosmology has been the photometric classification. Until recently, we think that's been solved, so we're really forging ahead. The supernovae will be big players in all of these other different probes of cosmology, like S8 and tests of gravity. And ultimately, these forecasts that I'm showing here should be better, right? These were binned analyses, so it's going to be even better than that. So we're really excited. So, muito obrigado.
Questions from the audience, from the presential audience first. I'll keep an eye on Zoom So what is Roman?
It's a space telescope. It's NASA's. I think it was converted. Microphone. Oh, it was one of these converted spy telescopes that is, you know, like a better Hubble.
So it's already in orbit, is it?
No.
Okay.
They basically rebuilt it.
Okay.
Yeah, NASA.
So it's time scale of 5-10 years.
It's further off than LSST. It's I think like late 2020s. Yeah, like
okay, so
2030 maybe. I think. Yeah.
Yeah, 5-ish,
Yeah.
10-ish. Okay, Raul first, and then Rogerio. So switch off your microphone, Dillon. Yes, Raul, please. Raul? Ah. No, there is another Raul who raised his hand on Zoom. First, and then Rogerio.
Hi, Dillon, can you hear me?
Please.
Can you hear me?
Yes.
No, you can't hear me. I'm speaking, but I'm speaking.
Yes, Raul,
But
we can hear you with a few seconds delay, but we have to keep our microphone off while you're talking, because otherwise there is echo. First, and then Rogerio.
I'm trying to say something, but do you hear me or not? No, you can't hear me. I'm speaking, but speaking.
Raul, we cannot talk while you talk, otherwise there is echo, but we are listening to you. Okay. We are listening to you.
I'm trying to say something, but okay. So now I'll ask my question in one go directly. Sorry about the about the echo. So Dillon,
Raul, we cannot talk while you talk, otherwise there is echo, but we are listening to you.
No, okay. This is not working. Sorry.
Raul, we can set up a time to talk. How about that? Because I want to talk to you anyways.
Rogerio, you want to try?
I will try. So first, congratulations, Dillon, for the baby, 2 babies maybe, or the several babies, and for the great work that you have done. And my question concerns the covariance matrix. So this 1,000, roughly 1,000 by 1,000 matrix, that's probably the 18 surveys in different filters. Question is twofold. So how do you compute the covariance matrix between different experiments, and how do you guarantee that's positive definite?
Yeah, good question. So we propagate the covariance for the different surveys by using our entire pipeline. So if we have some uncertainty in the actual supernova model itself, or the light curve model that does the fitting, we change our assumption in the very beginning of our analysis, and we fit all of the light curves of all the 18 different surveys with the new model, and we, for each supernova, can determine a perturbation in distance. And it's essentially agnostic to the surveys. Once you've calibrated them all, you can treat their photometry very similarly and propagate systematics to all of them simultaneously. There is some subtlety to that because we expect these biases in the observables due to the observing programs of different surveys, and we treat those systematics slightly differently, and we have to take more care to do them by survey. But the majority of the systematics affect all the supernovae simultaneously, and we do it from a top-down. Yeah. How do we ensure it's positive definite? Yeah, that's what I was getting at. It's easy to say don't bin, but when you have an extremely large matrix, you're susceptible to that. We came across just a couple of examples, and they turned out to be when the light curve fitting, for example, had fallen into a false minimum, and that actually alerted us to some issues that we had to fix in the fitters and various points in the analysis. Yeah, that took a couple months to really understand why the positive definiteness actually led us down a couple paths to understand our data better. It is difficult. It's actually, I'm not sure that is even guaranteed to always be positive definite, but for us it ended up being after we saw, stumbled across all those examples. If it's not, there is a potential solution. Also, with 1 million supernovae in LSST, we're not inverting those matrices anyways. What we're working on is, I think it's like a paper called If Binning is Sinning, is Rebinning Redemption, or something like that, where basically you take your data set, don't bin it as a function of redshift, but bin it as a function of other properties of the supernovae in as many bins as you can really afford, to not collapse down as much of the information as possible. Basically, retain as much of the information as you can and keep it computationally feasible.
I'm gonna read the question by Raul. Really interesting that you seem to have solved the issue of the correlations between the supernovae and the host galaxy. If I, Raul, understood this correctly, then this correlation is simply due to the dust in the galaxy, which does correlate with the properties such as star formation rate, age, etc. It is amazing that you guys were able to separate that property by itself, especially since dust varies so much inside the galaxies. How did you manage to measure the dust at the host at the location of the supernovae?
Yeah, good question. We don't. So there have been studies that have looked at, is the correlation in the inferred luminosity as a function of host properties stronger if you look at the local location around the supernova? And it's actually been not so clear that it is much stronger, if at all. So there's a couple of pieces to that question. First of all, I may not have been careful enough with my words to say that we don't even know that this dust is the circumstellar dust or the interstellar dust. It could be right around the supernova, or it could be just the general dust properties of the galaxy. I would say that because it correlates almost as strongly, it may correlate just as strongly with the global measurement of the mass or the dust properties that we have readily available at high redshift. I would put my money on interstellar dust. The other thing I would say is, I think people like Eddie Schlafly and Doug Finkbeiner, who do Milky Way dust, would say that it doesn't vary that much, at least in the Milky Way, across the Milky Way. So what my argument is actually, I think, consistent with Eddie and Doug, that the dust properties are relatively similar within the galaxy, but if you look at another galaxy, it can vary widely. And the key point here, when I'm talking about variation, I'm talking about the dust law, RV. I'm not talking about the amount of dust. I'm just talking about the color luminosity relation. That was the key thing into realizing that's what was biasing our measurements. Yeah.
I assume Raul is satisfied with the answer, otherwise Raul please type something. But in the meantime, Raul typed the second question. So I asked the second question while waiting for feedback to the first one. So if binning is sealing, then combination is damnation. We really ought to not combine.
Yeah.
Right?
Yeah. So that's why I pulled up this slide here. So we don't. So nowhere in the paper, the Pantheon Plus paper, do we combine SH0ES with Planck. We only combine Pantheon Plus, which is just the supernova, the uncalibrated relative distance indicators. So yeah, you're right.
This microphone is without battery. Any more questions from the audience? This is without battery.
Thanks for talk. So at the beginning you mentioned that you're using 42 Milky Way SFAs in your analysis for the calibration of the distance ladder, right? Are you using Gaia data as well in this?
Yeah, so this is using, the Cepheid analysis uses the latest Gaia update. Yeah. Okay, so we got a thank you from Raul. So maybe that's it.
Okay, for people in Zoom land, unless you have some last minute question, we close the seminar basically in 5 seconds, 4 seconds, 3 seconds. Okay, thank you, Dillon, once more, and see you next Wednesday for the next meeting of the Journal Club.